So today we're going to do meteorology for pilots. It's kind of like weather theory. So you want to understand what causes the weather, as well as how to interpret it, how to read it, because that's going to help you make safe decisions in the end. So resources for this one, chapter 12, which was the reading for this lesson. And then another one I recommend is the Aviation Weather Handbook. It used to be 2 manuals, and then a couple years ago they combined it into one, so now you have like one pretty thick book. Again, it's an FAA publication, so you can download it for free. But like the Handbook of Aeronautical Knowledge has like a really brief introduction to a lot of these topics, and then the Weather Handbook goes into a lot more detail. So looking at the structure of the atmosphere, you don't necessarily need to memorize every one of these layers of the atmosphere, but at least a basic understanding of where the weather is going to occur and how that's going to affect your flight. So atmosphere contains life-giving gases. We live in the troposphere. Commercial flights are going to occur in the stratosphere. So within the troposphere, most of the Earth's moisture is contained down here. This is where weather patterns occur. Above the troposphere, you have something called a tropopause, which is kind of like a cap layer that holds all the moisture into the troposphere. Above that, you have the stratosphere. So most commercial flights are going to occur within the lower layer of the stratosphere. Above that, you have the mesosphere, and the thermosphere, and exosphere. And we've seen this slide before, looking at composition of the atmosphere. So composition does not change with altitude, but the pressure does. And our first step to understanding weather is to understand atmospheric circulation. Most weather occurs because of uneven heating of the Earth's surface. So like it says right there, the dynamic or changing part of weather or the atmosphere occurs because of uneven heating of the Earth's surface. So what that means is the equator has the most direct contact with heat and the sun and the longest exposure. And so that creates temperature differences, and those temperature differences create circulatory patterns because warm air is less dense. So air at the poles is cold and more dense. Air at the equator is going to be warm and less dense. And so that creates a global circulatory pattern like this, going from north to south down to the pole, and then from south northward up to the equator. So that's not the only thing affecting our weather, and we're going to look at a few more things that play into that. It's a few layers that cause wind and weather. Atmospheric pressure, you can think of that as the weight of a column of air. So at sea level, atmospheric weight is going to be about 14.97 pounds. And if you go up to 18,000 feet, about half of that. So it's the force exerted by the weight of air, and it's going to change. So a couple things can change it: temperature, altitude, air density. Different ways to measure atmospheric pressure. So you may have seen, this should look familiar to you, 29.92. So that's based off of a mercurial barometer. So if you remember really old thermometers, the warmer something is, you see the mercury kind of travel within a thermometer. A mercurial barometer works similar in that part of that mercury is exposed to the atmosphere, and when atmospheric pressure increases, that forces mercury up the tube, and on the side you would read how much pressure that is. When pressure decreases, less force is exerted on the mercury, and that's able to go or drop within the tube. Another method is an aneroid barometer. So this should look familiar to you after looking at the flight instruments. So this is a sealed aneroid cell or wafer. And depending on atmospheric pressure, it's going to compress those wafers or diaphragms or allow them to expand. And then that's going to be read on a dial here. Differences between these two: obviously you're not going to be traveling with mercury in your backpack or something. So an aneroid barometer is a little more travel friendly, and it's easier to read on the handle here, but it is less accurate than mercury. So ISA, we talked a little bit about it. So that stands for International Standard Atmosphere, and that's been established to develop a common reference. So obviously aviation exists across the globe, weather stations exist across the globe, and so they need a way of standardizing measurements. And so they're always going to translate inches of mercury to sea level pressure, which is read in millibars or hectopascals. So we know that standard in inches of mercury is going to be 29.92. Reading that in millibars, it's 1013.2. So along with global circulatory patterns, we have the Coriolis force. So because the Earth is rotating, wind or pressure doesn't travel in a straight line, it gets deflected. So in the northern hemisphere, it gets deflected to the right, and in the southern hemisphere, it gets deflected to the left. If you're looking kind of at a top-down view of the globe, if your wind are these black arrows and it's rotating this way, it's going to cause a deflection to the right of the wind. Another way to look at it is, you guys remember this from the playground. If you were to roll a ball to somebody on the other side, the ball would just kind of form an arc and get deflected. It wouldn't travel directly across to the next person. And there's global circulatory patterns and other things that affect that. So this is just one component of circulation. Next is a frictional force. So there's, along with pressure gradient that we looked at with uneven heating of the Earth's surface and the Coriolis force, those combined work to create wind. So not just a single thing creates the wind, it's a combination of pressure gradient and Coriolis force. So air travels, like we talked about, gets deflected to the right, so it's traveling west to east. And close to the Earth's surface, you have surface friction, which is going to slow down the Coriolis force and cause it to deflect in a different manner. But at higher altitudes, it's going to follow these pressure gradients or isobars that we'll look at a little bit more next lesson. So closer to the surface, wind tends to be slower. And as you get up to higher altitudes, you'll have winds that get into up to 100 miles an hour, 200 miles an hour. And as you get close to the surface, it's 15, 20 miles an hour. So it gets pretty slow. And air is always going to travel from high pressure to low pressure. So regardless if we're talking about wind or aircraft systems or anything, pressure always wants to go from high to low. The circulatory pattern around high pressure is going to go clockwise and downward. And around low pressure, it's going to go counterclockwise and upward. So easy way to remember that is make an L with your right hand, point your thumb up, and the way your fingers curl is showing a low pressure gradient. So low pressure goes counterclockwise and upward. And then if you flip it, that's high pressure. So it goes downward and clockwise. So global wind patterns, we looked at the global circulation going from the poles to the equator, gets warm, rises up, cools down, goes back to one of the poles. Those are further divided into cells. Again, you don't need to memorize the names of all these cells. It's just basic understanding. So if the Earth is rotating this direction, it creates a deflection, which form different cells along the surface. So Hadley cell is going to be close to the equator. Then you have a Ferrel cell and polar cell. And so it creates smaller circulatory patterns rather than just one giant one that you would see like this. So now looking at local wind patterns, we have something called a sea breeze. So if we live close to the water, water retains its temperature a lot better than land. So water tends to be cool, especially near the Pacific Ocean. And so air near the surface of the water is going to be cold and dense. And then land is going to be warm and drier. So warm air is going to rise up into the atmosphere, and it's going to cool down and sink over the water. And over here you have cool, dense air, and that's going to replace the air that just left over here. So it's going to kind of create a vacuum or a low pressure area and a high pressure area over the water. So this is why typically during the day you have wind coming from the ocean, and at night the opposite happens. So land is going to cool faster than water, and water is going to retain some heat. And so the opposite occurs, where you get wind that goes from the land outward to the ocean, warms up over the water, rises, and that gets replaced by high pressure, cooler air that's over the land. So it's pretty consistent around here that during the day we get wind coming from the water, and then at night the wind shifts. It's not very strong, but at night the wind typically shifts, comes from the north, and goes outward towards the water. Other ones, same principle, but now we're going to be looking at mountains or valleys. So we have a valley breeze that the surface on a mountainside is going to get heated during the day. It's going to rise up and get replaced by cool air that's sinking higher up in the atmosphere. So it's going to create an upslope circulatory pattern. And a mountain breeze occurs at night, so it's the opposite now. So mountain peaks and the mountainside is going to cool at night and sink down to the bottom. And then it's going to get warm, rise up, and drop like this. Another one is Katabatic winds, also known as downsloping winds. So we can most likely compare this to the Santa Ana winds that we get here. So if you've ever been curious as what's causing that, it's going to be Katabatic winds. So you could have a cold downslope. So if you have snow on the peaks like you do here, that's going to create cold, dense air, and that's going to flow downward, down the mountain. A warm downslope is what we get typically with the Santa Ana winds. So what causes that is high pressure out in the desert, like Nevada area, and low pressure in California or off the coast. So high pressure wants to go where low pressure is, and so it carries warm, dry air from the desert. And as that wind crosses mountains, it compresses, speeds up, gets warmer and drier. And so it kind of accelerates, gets warmer as it travels across all the mountain ranges. And by the time it reaches us, we have really warm, dry winds. So we'll probably get some October, November. So usually it's pretty cyclical. We get it in fall and spring. It doesn't always mean you're gonna have to cancel like a flight lesson or something, depending on where you're at in training. If you're just learning to do like your takeoffs and landings, probably not like the best environment to go practice that when it's like gusting 40. So typically we'll postpone or something. But if you're a little more advanced, maybe like later stage 2 or stage 3, it's a good experience to go fly in this if it's within a safe margin. So atmospheric stability, it's usually compared to the rate at which temperature changes with altitude. Definition, it's going to be the atmosphere's resistance to vertical motion. So a very stable atmosphere is one that resists vertical motion. So if you have temperature that changes really quickly with altitude, that's an unstable atmosphere. If it's pretty consistent or changes very slowly, that's going to be a stable atmosphere. So stability is often compared with poor visibility, but really smooth air. Instability is going to be compared to clear conditions and really rough air or turbulent air. So since we're talking about the Santa Ana winds, typically it's really clear during those days, like you can see from here to LA. But it's really turbulent, it's really windy. And then other days like today, it was extremely smooth, but visibility was horrible. It was like super hazy, there's clouds off the water. Adiabatic heating and cooling occurs when there's a change in temperature with expansion or compression. And this should be familiar, standard lapse rate, how pressure and temperature change with altitude. So temperature should change 2 degrees for every 1,000 feet. We should have a decrease, and pressure should decrease 1 inch of mercury for every 1,000 feet. So you can look at this table and you can see that it decreases 1 inch of mercury and 2 degrees Celsius for every 1,000 feet. There's obviously some discrepancies, it's not perfect, but it's a standard way to measure it. There's something called temperature inversion, in which temperature would actually increase with altitude, and it's not uncommon. Usually it's going to lead to poor visibility below the inversion and an increase in temperature with altitude. So, common question. Hopefully you got C, since we just talked about it. So temperature inversion, you can expect an increase in temperature with altitude. Also talking about Still related to atmospheric stability is moisture changes. Probably saw this in science class years ago. So going from, talking about water, going from a solid state to a gaseous state, that's called sublimation. Going from a gas state to solid, deposition. Pretty rare that these will happen. You can usually associate this with dry ice, goes from a solid state to a gaseous state, which is why you want to be careful when you're transporting dry ice in an aircraft. Going from a solid state to liquid, melting, liquid to gas, evaporation, gas to liquid, condensation, liquid to solid is freezing. The outside ones, so top, sublimation and deposition, are less common. Everything in here should be familiar to you, and it all has to do with an exchange of energy. And we're concerned about this in flying because it's going to lead to things like icing, precipitation, all of which you need to be familiar with. Looking at moisture and humidity. So humidity refers to the amount of water vapor present in the atmosphere at a given time. And relative humidity is the amount of moisture in the air compared to the total amount that it can hold. So it's often used as, or it's often read as a percentage. So if you paid attention to the news or looked at like a weather app, they'll say 60% humidity. And so that's just a portion of how much it can hold at that temperature. Now, dew point is the temperature at which the air needs to reach to become 100% saturated. So typically when you listen to the ATIS, it'll read temperature and dew point. Reason why we look at that is because what the temperature currently is and what the temperature needs to become 100% saturated. So the reason why we're concerned with that is because let's say the temperature is 20 degrees Celsius and the dew point is 10. If the air cools to 10 degrees, that means you're gonna have 100% humidity or saturation. And that's gonna lead to fog, low clouds, precipitation. And so the closer those numbers are to each other, you start to get a little more concerned. So within about 5 degrees of your dew point is when you start to get the symptoms of saturation. So fog, dew, precipitation. So that's called the temperature dew point spread, is the number or the difference between those two. And here's a way to determine your cloud base. So looking at, we'll use Celsius, because most of our weather reports are given in Celsius. So you take your temperature dew point spread, divide that by 2.5, multiply that by 1,000, and that'll give you the height of your clouds above ground. So using that same example, if your temperature is 20 degrees Celsius and the dew point is 10, divide that by 2.5. So 4 times 1,000, 4,000 feet. So your cloud bases should be at 4,000 feet based off of that spread. So what that's saying is at 4,000 feet, the temperature decreased to a point at which you can form clouds. So a couple different ways you can reach saturation point. When warm air moves over a cold surface, surrounding air temperature of the surrounding air decreases and reaches saturation point. When cold air and warm air mix, and we're going to look at a few different instances in which you would see these. Number 3, when air cools at night through contact with the cooler ground, air reaches saturation point. So this is a type of fog that we'll look at. When air is lifted or forced upward in the atmosphere. So looking at clouds, clouds are going to be grouped or based off of their height. So there's 4 different groups. Looking at the bottom here, we have low clouds. Then we have middle clouds, high clouds, and the 4th group is clouds with extensive vertical development. So they're defined or grouped based off of their altitude. So you can usually tell what type of clouds they are just so when you read them, you kind of have to dissect the phrasing of it based off the prefix and suffix. So anything with nimbo as the prefix refers to rain. Alto is going to refer to middle clouds, and then cirro is going to be high clouds. Anything with the prefix cumulo is usually referring to thunderstorms or cumulus clouds. So most clouds in and of themselves aren't dangerous. They impede visibility, which we need to maintain as VFR pilots. But for the most part, you're going to be concerned with cumulus clouds or cumulonimbus clouds, because those are going to be the ones leading to strong turbulence, thunderstorms, lightning. So look at the top here, how precipitation occurs. First starts with evaporation. So there's a water source, water becomes evaporated. Water droplets form and they adhere to particles known as condensation nuclei. Once those droplets become large enough or too heavy to remain suspended in a cloud, they begin to fall. So it's going to lead to like rainfall, snow. Easy way to think about it is like water on your windshield. If you ever watch water droplets collide on your windshield, once they become too heavy, they begin to just fall down the windshield. So same thing occurs in clouds. Another type not listed there are lenticular clouds. So you can see these disc or almond-shaped clouds above the mountains sometimes. Not that you're paying attention, but typically July and August is when you'd see these form over the mountains out here. These are usually associated with mountain waves or severe turbulence going over mountains. So if you see these, don't go near them. Mammatus clouds, you'd see these associated with thunderstorms too. So they're called mammatus because they kind of look like udders. So they look like mammary. Next we'll get into types of fog. So again, this is air that has reached saturation point, close to the surface. So the first one we'll look at is radiation fog. And that's going to happen overnight as the air close to the ground reaches, is cooled, reaches dew point. And for this to happen, it needs to be in a cool, stable area, so no wind. So light to no wind. If there is wind, it'll dissipate. Doesn't tend to linger very long. So as we talk about fog, it really helps you remember what the names are if you think about what is occurring to make that fog form. So radiation fog happens because the heat radiates from the surface, and so the surrounding air close to the ground cools, reaches dew point, and forms fog. Next is advection fog. So it's going to be caused by a low layer of warm, moist air moving over a cooler surface. So this is what happens with our marine layer that we get every day. So in the evening, water is going to retain heat more than land. And so you have warm, moist air, travels over land, cools, reaches dew point, and you get fog. So this one does kind of thrive on wind. Radiation fog needs calm conditions. Advection fog needs some wind, and it pushes it inland a little bit more. So some days it hardly reaches kind of where we're at now. Other days it reaches all the way inland, reaches to like Inland Empire. And that all depends on the strength of the wind. So upslope fog, you're gonna have moist, stable air that's gonna be cooled as it goes upslope. So as it gets higher in altitude, traveling upslope, you're gonna get fog. This one does require wind as well. Obviously need something pushing your wind upslope. Eventually though, it gets high enough where it just becomes stratus clouds. It's no longer fog. Other one, frontal fog. So we haven't talked about fronts yet, but we will here in a minute. So fronts are going to be the boundary layer between different air masses. And so when those air masses come together, you could get frontal fog. Steam fog requires an evaporation of precipitation. Different types of precipitation. Yes, we talk about this. So drizzle, small water droplets, in case you wanted to know the actual measurement, less than 0.02 inches. More importantly though, rather than the terms, is what causes these. So rain, water droplets become too heavy to remain suspended. Virga is evaporated rain. So if you've ever noticed underneath like a really dark cloud or where you can see where it's raining, it looks kind of hazy or dark underneath. And that's because as rain falls, some of that water evaporates again, or it reaches the ground and evaporates. Ice pellets, rain falls through an inversion, so a warm layer freezes before reaching the ground. Hail, formed by water droplets that freeze through a cloud and go through a cycle of updrafts. They fall, refreeze. And snow just remains frozen. So it makes a little bit more sense looking at this table here to the right. So when snow falls, precipitation remains frozen all the way to reaching the ground. Something like sleet, snow falls, melts, refreezes again, and reaches the ground as sleet. And then freezing rain goes through a layer of goes through a deeper warm layer and then a shallow cold layer. And so there's a moment where that thaws and then refreezes as it reaches the ground. So I looked at these two. Freezing rain, kind of a different image or depiction of this one. So it needs a longer time where it's melted, in which it just becomes rain again. And then once it reaches the ground, at the surface, it's going to be below freezing. And so on impact, that water freezes again. So if you've ever seen videos like on the news or social media where people, their car looks almost frozen over, they roll down their window and then they can just punch the ice out of the window, that's freezing rain. So rain fell, hit the car, and then froze. So it forms a really smooth, glossy type of ice. And then rain doesn't have to be frozen, but at some point that precipitation was frozen and then goes through a warm layer and reaches the ground that's also warmer or above freezing. So air masses, which I just mentioned, is a large body of air with uniform temperature and moisture content. So usually it's going to bring with it the contents of where it's coming from. So if it comes from like a tropical area, it's going to bring warm, moist air with it. If it comes from like a polar area, it's going to bring cold, dry air with it. So it's known as its source region. And then a front is going to be the boundary between these regions or these air masses. So weather along a front is typically adverse or bad. You're going to have thunderstorms, rain, fog, shifting winds. So discontinuities are going to be the changing conditions that you can associate with fronts. So typically, whenever you have a front, you're going to get a change in temperature, change in wind, and change in pressure. So the wind direction is going to change, moisture content, and temperature. So recently, this was a checkride question for somebody that they were discussing weather during the test. And they said, what typically occurs along a front, and it's always a change in wind direction. So stuff does come up in real life. So different types of fronts. First one we'll talk about is a cold front. So a cold front occurs when a cold, dense and stable air advances and overtakes a warm air mass. So these are usually fast moving, 25, 30 miles an hour. And so it plows through, comes in contact with a warm air mass, and works like a snowplow. So it pushes the warm air mass up and over, so it kind of digs underneath it. So usually before that happens is you'll start to get cumulus clouds forming. As it passes, you can get towering cumulus clouds, thunderstorms, pretty bad weather. As it passes, you'll continue to get rain and dissipation of those thunderstorms. And the way you identify this, and we're going to talk about weather products, but it's going to be this blue spiky line. Now, warm air mass is the opposite. So you're going to have a slow-moving warm air mass or front that overtakes a cold one. So usually when this happens, it doesn't work the same manner in where a cold front goes underneath a warm front. The warm air mass kind of rolls on top of it. So as it does that, you could still get precipitation. There's always a potential for thunderstorms. Most likely we get stratiform clouds and precipitation or drizzle. So again, they're slower moving than cold front, and the warm air mass will go on top of the cold one. So if you remember, that's also known as an inversion. So you have cold at the surface and then a warm air mass above that. on that note talking about inversion. So it doesn't roll on top and just stay like that. It still pushes the other one out of the way and overtakes it, or replaces the area where it was. So eventually, this is what happens. It pushes this cold air out of the way and gets replaced by this warm air. Then we have an occluded front. So an occluded front, you can have two different types: cold front occlusion or warm front occlusion. So cold front is colder than the cool air is overtaken by the warm front. Just think of this as like a sandwich. So either way, on a cold front, you're gonna have cool air, a warm front trying to replace that, and then a cold air mass traveling fast and trying to overtake that. Opposite can occur. You can have a warm front occlusion in which you have warm air, a cold front overtaking that, and then a warm air mass behind it. So it's called occluded because it's isolated or kind of cut off and being sandwiched by the other air around it. Sorry, let me correct my phrasing. So this is a warm occluded front or warm front occlusion, and then a cold front occlusion would be the opposite, where you have warm air mass here and cold down here. And this is typically the weather you would get. So you get cold air and then warm air trying to overtake that, and then faster moving cold air behind that. So you get stratus clouds, and then as the cold air overtakes this warm air, you basically get a cold front here and thunderstorms. Then stationary front. So this is going when two air masses have relatively equal force and neither one is strong enough to overtake the other one. So they collide and they kind of just linger for a prolonged period. So usually whatever weather is occurring along a stationary front is going to linger for a few days over that area. And you could get a mixture of weather patterns from either cold front or warm front. So precipitation, again, always potential for thunderstorms. Like I said before, we're not exactly concerned with every type of cloud. It's not like you see a cloud in the sky and you're like, oh, we gotta avoid it by all costs. Obviously, there's certain regulations we need to adhere to maintain visibility or distance from clouds. But what we're primarily concerned with are thunderstorms. So thunderstorms are going to lead to pretty violent turbulence, hail, lightning, poor visibility. This could be associated with either rainfall or gusts. So in order for a thunderstorm to develop, you first need sufficient water vapor, a lifting mechanism, and unstable air. So you can kind of think about that as like the recipe for a thunderstorm. So you need all three of those things for a thunderstorm to develop. And then here is the life cycle of a thunderstorm. First stage is going to be the developing stage. It's going to be associated with primarily updrafts. So as that's building energy, you're going to have updrafts. You can still get lightning, and it's going to last for about 10 minutes during the stage. Next is the mature stage, in which you still have updrafts, but it's also associated with strong downdrafts. So this is going to be the most dangerous stage for us. So it's going to have pretty bad turbulence, really strong downdrafts, and then the dissipating stage, which is going to be primarily downdrafts as the thunderstorm releases all that energy. There's different types of thunderstorms. This is mostly related to how many cells a thunderstorm has. So you could have a single cell thunderstorm in which there's one primary body to the thunderstorm. You could have multi-cell, so there's kind of a group. A supercell, which is just explaining the size of it. I'd say more importantly, out of all this, what you want to be able to identify is something called a squall line. So a squall line is like a wall of thunderstorms. So it's multiple cells of thunderstorms that develop a fast-moving wall. So for us, it's hard to fly around thunderstorms. We can't really travel above them because they can go 20, 30,000 feet in the air. So we can't get above it, can't get around it, and if it's moving fast, it could be kind of difficult to outrun it. Just because they're intense, they move quickly. Embedded thunderstorm is particularly dangerous as you get into your instrument rating. So right now we avoid clouds, and so there's not necessarily a danger of embedded thunderstorms. But when you get your instrument reading, you're going to be intentionally flying in clouds. And so it's called embedded because it could be stratiform clouds, and they could be pretty innocent clouds that you're flying through, and then there could be a thunderstorm hiding within those clouds or embedded. So hazards with thunderstorms, which I mentioned before, really strong turbulence, hail. So the way that hail develops is that as precipitation falls, it melts, refreezes, and then gets sent through updrafts again. So it kind of follows a circulatory pattern of updrafts and downdrafts. And so something that starts off as maybe a small piece of ice accumulates more and more ice and eventually grows into a large hailstone. And then at some point, that hail could get thrown out the top of the thunderstorm. So that piece is called the anvil, which is like this overhanging part. So hail could get tossed out that way. So even if you're flying out here and you think you're in the clear, you could still get hit by a hailstone.
It does look like an anvil.
Yeah. So our safest bet is to avoid thunderstorms by at least 20 miles. Because even 5-10 miles away, you could still experience really bad turbulence and hail. Lightning as well. So lightning could damage your electronics, cause momentary blindness. So not good while you're trying to fly an airplane. Another one is tornadoes. Obviously, we don't get tornadoes here, but eventually you're going to be flying everywhere. And so because of the circulation that's caused by these updrafts and downdrafts, it could cause a vortex, and that eventually would lead to a tornado. Different types of turbulence. Low-level turbulence is just describing anything below 15,000 feet. Mostly it's going to be due to uneven heating of the surface, in this case just close to ground or local. Mechanical turbulence, anything that obstructs airflow. So we have lots of buildings surrounding an airport that could create turbulence coming into land or close to the airport itself. That could also be associated with mountain waves. So as air flows over a mountain, it could create turbulence. And then convective or thermal turbulence, people most often experience this as they're coming into land. Most airports, they have industrial areas surrounding the airport. So they go from flying over grass, back to cement, back to grass, to dirt, back to cement. And so those changes in surfaces could create thermals. So you could rise up, then sink, then rise up and sink. And so that's typically where students struggle a little bit when they're learning how to land the plane, is they're like, I don't know what happened, I just started climbing. And so it's usually because, oh, you flew over a freeway and then you flew over dirt. And so the plane goes up, then it wants to go back down. Frontal turbulence, so along the front, you're always going to get some sort of turbulence as wind changes direction and speed. And wind shear, we'll talk about wind shear in a second. Clear turbulence, usually higher altitudes, 20 to 50,000 feet. It's often associated with wind shear, which again, we'll talk about in a second. Because jets or commercial airlines fly in jet streams to kind of capitalize on tailwinds, they could get clear turbulence. This is usually what you see on the news or like social media, where like the drink cart is like on the seats and like people have like nosebleeds and like, we don't know what happened, there's turbulence. So it usually comes out of nowhere, where they lose thousands of feet really rapidly, and then it's pretty severe turbulence. Wake turbulence, which we talked about with aerodynamics, is when you're in the vicinity of other aircraft, creates vortex around the wingtips. And if you fly really close to an airline or behind one, you can encounter this type of turbulence. So this is wind shear. So wind shear is going to be a drastic shift in speed or direction of wind. And so that could occur at any altitude. It doesn't have to be at the surface. A type of wind shear is called a microburst. Again, this kind of looks like the dissipating stage of a thunderstorm, where it's just downdrafts. So this occurs low to the ground, and it's going to be very strong downdrafts, up to 6,000 feet per minute. So for us in a small plane, or any plane close to the ground, it's really dangerous because you encounter a very strong headwind as you enter it, which is going to lead to better performance momentarily, then you're gonna have very strong downdrafts that's gonna push your airplane down, followed by a very strong tailwind. And so as you get into a tailwind, you have less airflow over the aircraft. So now you're gonna have a drop in performance as you exit. So if this occurs close to the ground, you don't have enough performance or time to recover from it. Types of icing. So there's structural icing, which is what we're going to focus on right now. We talked about carburetor icing before, or induction icing. So the first type we'll talk about is called rime ice, spelled a little bit different than you've seen before. So rime ice looks like this. It's going to be rough textured and white. So this happens when water strikes the aircraft and freezes on impact. And so you need really cold conditions for this to happen. So when it does, because it freezes so quickly, it traps air inside the water or in the ice, and it makes it look white. So it kind of looks like popcorn ceiling in a house. Next is clear ice. So this one occurs in a little bit warmer temperatures where water strikes the aircraft and smears across the surface and gradually freezes. So because it's a more, happens a little more gradually, air is able to escape it, and it forms clear sheets over the aircraft. So this is going to actually disrupt airflow considerably more than rime ice because it can build up a little bit thicker, and it's going to occur on like leading edges and narrow surfaces. So anything with a narrow surface, like leading edge of your wing, struts, landing gear, spinner, you can get icing built up on those. Next is something, this is a type of clear ice. It's called supercooled water droplets, or large droplets. So it occurs with larger water droplets, and it takes even longer for them to freeze. And so in this case, they could travel longer distances before it freezes. And so the point at which it builds up ice could be out of reach of de-icing equipment. So some planes have something called boots, where it just inflates and breaks ice off of control surfaces. Something called a weeping wing, where it'll release a fluid over the wing to melt ice. So it could be out of the reach of those and eventually disrupt airflow over the aircraft. And you can stall or lose control of the aircraft at lower airspeeds. So this one gets pretty thick. You can see how thick that is on like the windshield wiper right here and like the cowling. You get mixed ice, so it's going to be due to a combination of conditions where you go from like warm to cold, or I'd say cold to a little bit warmer temperatures. You can get a combination of clear and rime ice. So concern with ice in general is not due to weight. Oftentimes people think, oh, I'm building up ice, the airplane's so heavy it can't fly. It's more to do with airflow. So as you get anything that disrupts the smooth flow of air over the wing is going to decrease your performance. So the airplane could stall at a lower airspeed, or stall at a higher airspeed, and you could lose control if it's on control surfaces. So it's not an uncommon statistic that you could hear in like crash reports. Usually it's related to flying into icing conditions intentionally. So people think, oh, we'll be fine, we have all this de-icing equipment, and it just builds up faster than they can melt it or get rid of it. Or improper pre-flight. So maybe there was ice built up on the plane before they even took off, and so they go to take off, the plane won't climb, and then they crash soon after. So the same thing can occur with frost. So frost occurs like when you wake up early in the morning in winter and you notice there's like some icing on your windshield or something. I mean, it's less common here, but if you've lived somewhere else where you wake up to frost on your car. Same thing can happen in a plane. And so what you want to do is do a proper pre-flight, touch the surfaces, make sure there's no ice or frost built up on those. I don't recommend scraping it because that's going to kind of break up paint on the plane. Best thing you can do is just pull the airplane into the sun, let it melt.
So isn't like cold air also good for like engine performance too?
It is, but if there's enough moisture and it's cold enough, that could lead to icing. But yeah, overall cold air is more dense and better for performance. So kind of a fine line. So there needs to be enough moisture in the air, it's not going to occur out of the blue like you're flying in clear air and you just start getting ice buildup out of nowhere. Restrictions to visibility, pretty straightforward. Haze, like we had today, if you guys were driving around earlier today, it was pretty hazy, pretty hard to see. Smoke, again, we have forest fires, pretty hard to see if you're flying in the vicinity of those. Volcanic ash, I don't know of any volcanoes in our area, but can happen. Lastly, just looking at some warning systems. So because low-level wind shear is so dangerous, even for airlines, most airports now have an alert system that will advise you of wind shear. Either that or something called pilot reports. So if somebody encountered wind shear as they were landing, they'll report it to ATC, and that would be broadcast on ATIS as an advisory. So that way anyone in the area would know that wind shear was reported, whether departing or arriving at that airport. So that wraps up our lesson today. We're going to cover weather products or weather services next time. So thanks for coming. If you have any questions, just let me know.